Inclusion, exclusion, which not only is tons of fun, but it's something quite useful. We will use it to count onto functions for finite sets A and B. You might also see it in probability, where it's another, I would say, big use of inclusion-exclusion in a probability class. Well, let's talk about so far what we can do before we jump into today's lesson. Let's say A and B are finite sets. So we can count first of all the number of relations from A to B. We can count functions from A to B. We can count one-to-one functions from A to B. If, let's say, the cardinality of A is strictly less than the cardinality of B, or I could really say less than or equal to, but I will just say less than for the moment, we do know the number of onto functions. This, in fact, let me write from A to B. We have discussed in more than one video, although we proved it in the last one with the pigeonhole principle, if the cardinality of A is strictly less than the cardinality of B, there are 0 onto functions. Okay, well, we would like, and we will today, figure out when the cardinality of A is bigger than or equal to the cardinality of B, the exact number of onto functions. And we will do this through inclusion-exclusion. But before I do, let me give you a reminder about, because we have discussed inclusion-exclusion when we have two sets, certainly. So let's recall, if we have A and B finite sets, again, same setup, finite sets. But in this case, I'm not counting functions, relations, or anything like this. I'm just thinking about cardinality of A, cardinality of B, cardinality of the union. And the picture we associate to this is a Venn diagram like this. Here's A, here's B. And we know that the cardinality of the union, you can't just add the two cardinalities. Well, you can if they're disjoint, but that's not the general case. It's cardinality of A plus cardinality of B minus the cardinality of the intersection. And this we discussed, okay? How do we get this formula? Well, you think about adding, right? You add up all the elements of A, then you add up all the elements of B, and you notice when you do this that everything in the intersection has been counted twice, right? Once when you counted A, once when you counted B. So you must subtract off everything in the intersection one time so that everything in here is counted only once. And this is where this formula comes from. And we use this. For example, well, maybe I'll mention what this is called. This is called the principle of inclusion-exclusion. I'll do an example, and then we will talk about when we have more than two sets, and that's really what's new. The principle of inclusion-exclusion. And this principle for two sets, as I mentioned, this we have done, but let's do an example where we use this in counting. For instance, if I think about my universe out here, U, this U consists of, say, I'll write it in set builder notation, positive integers, such that X is less than or equal to 100. Okay, that's my universe. And then I could call this A, and this B, where A is the set that's divisible by 3. B is a set divisible by 5, like this. Write it like this, divisible by 3. B are the ones that are divisible by 5. And then what we want is, it's an OR, so we want this. And so we just count the number of things in A, number of things in B, number of things in the intersection. It's exactly this inclusion-exclusion. What's the biggest integer less than or equal to 100 divisible by 3? It's 99. So we'd have 99 over 3, which is 33. This is the cardinality of A. And the integers are 1 times 3, 2 times 3, 3 times 3, out to 33 times 3, like this. And then the biggest integer less than or equal to 100 divisible by 5 is in fact 100. So this is 20. This is the cardinality of B. What's the biggest integer less than or equal to 100 divisible by both? Well, to be divisible by both, so here, A intersect B, this says you're divisible by both, or equivalently, you're divisible by 15. 15 times 3 is 45, another 3 is 90, another 15 is 105, that's too big. So we have 15 times 6 is 90, and that's the biggest one. So we would take 90 over 15, which is 6. This is the cardinality of the intersection. And then we use the formula that was down here, and I erased for the union. This here is, well, it's 33 plus 20 minus 6. 53 minus 6. We have 47. Okay? Using inclusion-exclusion for 2 sets. Okay? It's a counting tool, right? Now, let us discuss 3 sets, and then we will work with how is this going to get us to counting on 2 functions. So let me discuss the principle of inclusion-exclusion for 3 sets, A, B, and C. Or maybe in fact I will now, instead of saying A, B, and C, I will use indices. So suppose we have 3 sets, A1, A2, A3, and these are finite sets. And I switched to this because we will state it more generally with n sets. So that's why I switched from ABC to A1, A2, A3 like this. Okay, now I can't really draw Venn diagrams past 3 sets, but I can for 3. Would be something like this. This is one that shows every possible overlap. This would be A1, A2, A3, and the number of things in the union. Okay, this is inclusion-exclusion, excuse me. And it's the same idea. It really comes from you include all these and you exclude, that's subtracting, and then you include and then you exclude. You include, you exclude. It's a bunch of adding and subtracting that comes in this formula. So let's see what this is with 3 sets. Well, the first thing I would do, you see I would add up everything in A1, A2, and A3. So I have cardinality of A1 plus cardinality of A2 plus cardinality of A3. And just like when we had only 2 sets, now what's happened is I've added A1, added A2, added A3. So everything, for instance, in here was counted both by A1 and A2, right? And similarly, everything in the intersection of, this was counted A1 and A3. I misread my index. Everything in the intersection of A1 and A2 was counted twice. So everything here in this red has been counted with A1 and with A2. And finally, everything here was counted with A2 and with A3. Okay, so we need to subtract, just like we did with two sets. So we subtract the number of things in this intersection minus the number of things in this intersection minus the number of things in, A2 intersect A3, like this. So far, what have I done? Well, here, here, and here, I subtract, subtract, subtract. Now, what's the problem? Okay. What happened? Everything so far, if you are in this that's just blue, we added it 1 2 times, we subtracted it 1. So now it's been counted the number of times it's there, which is 1 time. Everything in just this green, we added it 1 2 times, subtracted it 1, we're good. Everything in just this red, we counted it 1 2 times, subtracted it 1, we're good. But this is not the end of the formula, because notice here in the intersection of all three, what's happened here in this region? Well, let's go back to the beginning. Everything that's in A1 and A2 and A3, we counted it for A1, 1 time, for A2, 2 times, for A3, 3 times. Then we subtracted off for A1 intersect A2, subtracted off for A1 intersect A3, subtracted off, so it's in each intersection. It was added 1 2 3 times, subtracted 1 2 3 times. So now we haven't counted this at all. We must add it back. We add in A1 intersect A2 intersect A3, this cardinality. And this is inclusion-exclusion for 3 sets here. Now, as you can imagine, it gets more complicated when you go to 4 sets, 5 sets, 100 sets. You keep adding, subtracting, as I mentioned, include, exclude, like this. I don't want to get to that level of abstractness just yet, okay, because it will be fun when we do. But first, I want to use this. Now, how am I going to use inclusion-exclusion for 3 sets? I mentioned a big goal, we are doing this, is to count onto functions. So, let's suppose the cardinality of A is N, and the cardinality of B is 3. And, well, we know in order to, if N is less than 3, we have no onto functions, right? So if N is 0 or 1 or 2, there's no onto functions. So let's suppose here that N is bigger than or equal to 3. Okay? Now, we will count onto functions F from A to B. And how am I going to do this? Well, guess what? Inclusion-exclusion, but it's a little bit sneaky. I think it's a little bit fun, but it looks a little bit abstract at first. So just hold on for a second. I'm going to define some sets, and it may not be obvious how I'm going to use them until I erase and come back up here. So let me define. I'm going to define 3 sets, C1, C2, and C3. And you see we have this stated for 3 sets, so I will be using this formula with C1, C2, C3. Okay? Well, C1 is going to be all functions such that, well, before I do this, let me just give some names to the elements in B, excuse me. So let's suppose B equals B1, B2, B3. And now I can define my sets. This is all functions such that B1 is not in the image of F. And this one is all functions such that B2 is not in the image of F. And finally, this one, maybe you can guess already, this is all functions, such that B3 is not in the image of F. Now, you might be wondering, what are you doing with these? I thought you wanted onto functions, and none of the functions in C1, C2, C3 are onto. This is why I said just hold on for a minute, because I will get there. So let me erase all of this up here, and I'm going to draw a picture, and we will figure out where the onto functions are in all of this. Okay, maybe before I draw a picture, let me have one more thing that I put down below, because I do have space. I need a universe. So my universe U is going to be all functions. This is all functions. And also one thing we know how to count this. Well, I'm running out of space. Maybe I'll do it above. U is the one thing we know how to count right now, right? Well, and some of these, as we will discuss. We don't know yet the number of onto functions from A to B. That's what will come out of this calculation. Okay, so let's draw a picture. It's just an abstract Venn diagram at the moment. This is C1, this is C2, and this is C3. Okay? Now, we have to make some observations. This is all functions. Notice here, this C1 union C2 union C3. What is this set? Well, this says that either B1 is not in the image, B2 is not in the image, or B3 is not in the image. So this contains all functions F from A to B, such that the image of F is not equal to B. Right? Because, well, if these aren't equal, we know the image is always a subset of B. And if these are not equal, it means there's something in B1 that's not in the image, right? And that means either B1 is not in the image, or B2 is not in the image, or B3 is not in the image. So this is what's in this union. Therefore, if we want the set of onto functions, so the set of all F from A to B, such that F is onto, this is equal to you take the universe and subtract off this. Okay? Now this is how we're going to count it, because we can count the number of things in U. I started 2 down here and then I waited. And we can count this using inclusion-exclusion. Together we will get the number of onto functions. Okay, this is fabulous. So now let us count the number of things in U, and maybe I will even go down here to do my little side work. Here, right? What is a function from A to B? Well, if A, again, maybe I'll put this here, A is A1, A2, A3 to AN, what I need to do is specify F of A1, okay? Specify, this we have discussed, but it's important enough in this argument to discuss it yet again. I specify F of A1, F of A2, F of A3, and so forth, F of AN. Then I have a function. And B has 3 things, so I have 3, 3, I have 3, 3, 3, 3 possibilities. Each element goes to either B1, B2, or B3. So I have 3 for each. We have a total of 3 to the n. Okay, so the number of onto functions this is going to equal, well, we have 3 to the n minus, I'll write it this way, C1 union C2 union C3. Now let's count. Let's think about the cardinality of C1. Well, this is all functions, but B1 is not in the image. So what happens here? We no longer have 3 things to choose from, etc. We can only have 2 things. Either f of A1 is B2 or B3. B2 or B3, B2 or B3, like this. So the number of things in C1 is 2 to the n. And generally, that's true for any of these, right? Same thing for C2, same thing for C3. We get 2 to the n because if, for instance, if B3 is not in the image, then you either put B1 or B2 in each one of these. You have 2 options for each value can go to one of 2 things. Certainly can't go to both. That wouldn't be a function. Okay, well, so far, so good. We have a minus. There's 3 of these. So we have 3 times 2 to the n. That's for the individuals, right? Then I have to subtract off the sum of things like this. C1 intersects C2. We have C1 intersects C3. And C2 intersects C3. This would be the next term, right? I add up these, okay? Then I subtract these, and then at the very end, I add back the intersection of all 3. Well, here, C1 intersects C2. This says B1 and B2 are both not in the image. Well, there's only one function like this. It's where every single thing here, you only have one option, here, here, here. Now I'm working with this case. Maybe I shouldn't have it down here because it looks like I'm still counting all functions. But it says you just map everything in A to B3, and you don't have any other choice. Similarly, there's one here. This one says you map every element of A to B2, and this one says in this set, there's only one function, is where you map everything in A to B1. Okay, so these are 3. The last part of this of inclusion-exclusion would be counting. Okay, I will still leave my set C1, C2, and C3 up because we're using those. The last part is, right, we have all singles. Then we subtract all intersections of 2. Then we add back this. Well, zero, right? Because what this says is you have a function from A to B, but B1, B2, and B3, they're all not in the image. Well, there's no functions like that, right? There's no functions. I'm trying to even think what that would say about the second coordinates. It just doesn't happen, right? B has 3 things. There is no function that avoids all 3 of them in the image. That just does not happen. This cardinality is 0. So this, when we add back in, this is why I'll put a parentheses, and then I'm going to erase some more, and I'll go back and talk about my Venn diagram. C1, C2, and C3, and here was our universe U. But now we know it's not accurate. It doesn't look like this because in here, this is empty. So they don't really intersect like this. And maybe this is when you realize, I'm going to erase. Okay, this is not an accurate picture. So maybe we have C1, C2, and then something down here, C3. The picture is more accurate, something like this, where now you see that any two sets intersect, but all three do not, right? It's probably not, you could probably do a better Venn diagram, but it's an illustration, okay? That it's more like this picture rather than the one I had drawn. Okay, well, now let us just distribute the minus sign. We have 3 to the n minus 3 times 2 to the n plus 3. So this we have counted. This is the number of onto functions when the cardinality of A is n and the cardinality of B is 3. Okay? Now, before I do anything else, let's just do a little sanity check, because I'm about to get a little bit more complicated, not only with inclusion-exclusion, but also with onto functions, and it would be really nice to understand what we have done so far before we move on. So let's just consider when n is 3. Okay, in this case, a function from A to B, they have the same cardinality. This is going to be onto if and only if it's 1 to 1. So we should get, because we know that this formula is just going to be the same as the number of 1 to 1 functions, we should get from this formula, well, we know the number of 1 to 1 functions. You have 3 choices for f of a1, 2 choices for f of a2, 1 choice for f of a3. This is 6. So we should get 6 from this formula. This is what I mentioned, it's a sanity check. Make sure that we both have the right formula and put it into light of something that is understandable. So here we would get, let's check, we get 3 cubed minus 3 times 2 squared plus 3. This should be 6. This is 27 minus, oh, I was about thinking that I didn't have it right. N is 3. Okay, now I have a better chance of getting it right. I knew it didn't look right at the beginning. 27 minus, okay, now it looks better. 3 times 8 is 24, and then plus 3. And you see here we do in fact get 6, okay? So this makes sense in terms of something that we know. When A and B are both 3, we do get the same number as if you just counted the 1 to 1 functions. Okay,